Now we're going to look at some more springs. This is section 7.7, day 2 in the packet. Comparing FA and the force of the spring graphically. Let's take a look at it this way. Here is some spring attached to some block. Say this is 0, and this is the negative direction, this is the positive direction, right? If I look at the force, my applied force, if I move this thing this way, then it has negative position, but I have positive force, right? Or rather, right, in order for me to move it this way, oh yeah, I'm pushing in the negative direction, and the position is in the negative direction as well, right? So we're down here. And then if I'm holding the block over here, I'm having to pull this way, and then the block is also this way. So FA versus X looks like that. But the force that the spring exerts, right, as I do this, so the force of the spring in X, as I move this way, the spring is pushing that way, even though I have a negative position. And the farther I go, the greater the force of the spring. So this looks like this, right? And then as I move this way, the spring is pulling back in the negative direction. And so the spring is exerting a negative force, even though I have positive position. So that graph is going to look like that. And so we have these two different graphs, applied force and the force of the spring. It's important to keep that in mind when you're doing these problems so you get the positives and the negatives working out correctly. Now, what we're going to do is we're going to derive the effective spring constant when we have springs in parallel or in series. Just key things to keep in mind. You want to think about this. If I have two springs and I attach one and then I attach the other one, am I going to get a larger stretch or a smaller stretch from those two springs? Right? So imagine I've got two springs of the same spring constant, and I hang a weight from each of them. Right? And so there's a certain force here. What's the force? The force is just whatever the weight is from these things. So Fg is pulling down. And so that means that these springs have stretched a certain distance delta x. Right? But when I put them one on top of the other, and I put this weight at the bottom, Fg, it's the same weight as this one, right, or this one. It's just only one. So that means they're both experiencing that same force now. The tension is the same in both of these, and that means I'm getting delta x plus another delta x down here. By putting the springs like this in series, what's happening is I'm actually making one now weaker spring. So I'm going to get a smaller spring constant. But let's see how we can do that, right? Right. Now we're going to assume that we don't know if these are the same springs or not. We just got two different springs. But here, right, it's going to be, imagine I've got one weight attached, right, a weight attached here, a weight attached here. I get some delta x, and then one of these weights I attach here again, and now I'm adding up these two delta x's, right? So my equation for this one is F equals K1 x1. Okay, and then here I've got F equals K2 x2. These might be different springs, so I'm getting different stretches. And then down here, I'm getting F equals K total times x total. And this x total is x1 plus x2, right? And I want to know, how does this compare to these? So F equals K total. X total is x1 plus x2. Right. Now, x1 is going to be F over K1. And x2 is going to be F over K2. So if I plug that in here now, look at what I've got. F over K1 plus F over K2, because that's x total, so I plug this in here. And I divide this. F over K total equals F over K1 plus F over K2. And all my F's cancel out. So 1 over K total is 1 over K1 plus 1 over K2. So the way we find the effective spring constant when I have springs connected in series is like this. Right? And we just derived that. This is another derivation that you'll have to know how to do. You may have to do this on the test. One thing to keep in mind, if you only have two springs, there's a shortcut. If you only have two springs, right, only two, it's important, then K total is the product over the sum, K1, K2 over K1 plus K2, because that's what you would have to get. If you solved it that way with just two, right, you could find the common denominator, add the fractions, and then flip, and that's what you would get. But, let's see. Now, if you're adding them just two springs in parallel with each other, now it becomes a little bit different. Okay. Okay, so we imagine that we've taken two springs, they might be different springs, and we've attached them in some way, right, maybe different points here along the way, so that they both have the same stretch. Right. And so if I draw a free body diagram of this thing, I've got the force of gravity, the force of the first spring, and the force of the second spring. Right, so this is then the total, let's call this F total. This is the total downward force. And so I write out my rule here, right? F total is equal to F1 plus F2. Okay, well that's good, that's the forces. Now let's write out the Hooke's law for each of these things. So F1 equals K1 times X. Now the thing that I've done here, because of the way I've attached these springs, I've got the same stretch on all three. I just arranged it that way. And so I'm just going to leave this as X. F2 is K2 times X. And then F total is equal to K total times X. So I can take these and plug them in. So F total is K total times X. That's equal to, F1 is this, K1 times X plus K2 times X. Now I can just divide by X, and I get K total is K1 plus K2. So the effective spring constant when I'm attaching springs in parallel is just the sum of the two spring constants from before. Right, so this is another derivation that you might need to know how to do on the test. So the next slide is kind of a summary in general, right? The work is integral f dx. For Hookean springs, this is our summary. Example 1, we've got two springs, spring constants K1 and K2. They can be arranged either together, alone, in series, in parallel. And so what we're looking at is K2 is greater than K1. Which graph represents K1, K2, and these things? When you look at a graph, again, it's always important, what is the graph telling you, right? Introduce yourself to the graph, say, hello, graph. I see you are. And this one is F versus X. So then in that case, right, we know F equals Kx, so then K is F over X, and then that would be the slope of this graph. Rise over run, K is representing the slope. So the steeper it is, the bigger K is. And so what can be the steepest? How do I get the most K? By arranging them in series, right? Or in parallel. So in parallel, then D matches up with this. This has got to be D. And then they're always weakest when I have them together in series. And so that's got to be C. That's going to be this one down here, lowercase c. A little confusing. We've got letters on both of these. So let's just, you know what, let's just say this is in series. This is in parallel. And we know that K2 is greater than K1, so this has got to be K2 alone, and this has got to be K1 alone. So that's it. Let's take a look at example 2. We have an AP Physics student finds that he can stretch the same spring 1.3 times as far as an AP Bio student. It's a little, some fighting words. So we want to know what is the ratio of the forces they can apply, the force of the physics student compared to the force of the bio student, and then the ratio of the work done by each. Okay. Well, the force of the physics student to the force of the bio student. Well, F equals kx, right? So it's k, the same k, and then it's x times 1.3. We'll say x is how far the bio student can pull this. So the ratio ends up just becoming 1.3. So the answer to 1A, to part A is 1.3. But the work done, that's a little different now, right? Because the work done is the work of the physics student over the work of the bio student, an integral. Fx dx over Fx dx down here. And so this is from 0 to x. This is from 0 to x times 1.3. So this one's going to end up being, see, do we know? So we're just assuming this is kx. So this is 1/2 kx squared from 0 to x times 1.3 over 1/2 kx squared from 0 to just x, right? So these all cancel out, and this is then going to become 1.3x squared over x squared. So these things cancel, and I'm left with 1.3 squared, which is about 1.69. That's the ratio. He does 1.69 times as much work as the bio student. So good job, AP Physics student. Let's take a look at example 3. A 250-gram block drops 1 meter onto relaxed vertical spring. Okay, we've got something dropping. We've got a spring. This is going to be a conservation of energy problem, right? We want to start analyzing, like what category does this problem fit into? Is it a Newton's laws problem? Is it a work problem? Is it going to be both, right? Momentum. As we move on, the block becomes attached to the spring and compresses 4 centimeters before momentarily stopping. All right. So a bunch of things we're looking at here. A, what is the speed of the block just before it hit the spring? All right, so we imagine something like this. We're going to put the spring in a little bit of a well. Here's the block, and it drops 1 meter. That's the distance here. Okay, and then this is it at some later time, right? When it reaches compression, it compresses 4 centimeters before momentarily stopping. So this is it when it has compressed. And so this was 0.04 meters from here to here, right? Okay, so anyway, let's do A. We can do this a couple of ways. We can do this as a, MGH. We could do this VF squared equals VI squared plus 2A delta X, whatever you want to do. If we say that MGH equals 1/2 MV squared, M's cancel out, so you get 2GH, the square root of that is going to be the V, and so you get 2 times G, so 10 times 1, it's about, what is that, 20? Square root of 20. So this is going to be 4.47 meters per second. Okay, and then B now we're going to do this in terms of gap C. B, we want to know the spring constant. Okay, so what do we have at first? We're going to take it from the point where it reaches this here, so kind of between these two. The point when it reaches this point, then it has kinetic energy and potential energy. So if I'm looking at gap C, then I've got, right, K plus UE plus UG equals K plus UE plus UG. When it just hits the top of the spring, it doesn't have any elastic potential energy, but it does have kinetic and some gravitational potential energy because it's still above a little bit, right there. Later on, when it comes to rest here, these are out, and I only have elastic potential energy. So I have 1/2 mv squared plus mgh equals, and then this is just 1/2 kx squared. And I know all these things, so then I can substitute them in and find what k is. Notice also 1/2 mv squared here is equal to this from before, this mgh. So we could even put that in. Might make things even a little bit easier, right? But if we leave this, I can multiply everything by 2. I just want to simplify as much as I can. Plus 2 mgh is kx squared. So this is going to be mv squared plus 2 mgh over x squared equals k. I plug in my numbers here. M is 0.25. This is going to be 20 total, right? The square root of 20. 2, m again, 0.25. G is 10. H we can use as 0.04 because we're talking about this height now, right? As it's hitting the spring, so 0.04. And then x squared is also 0.04. And you square that, and it ends up coming out to about 3.3 times 10 to the third newtons per meter. Okay, now if the speed at impact were to double, what would be the maximum compression in the spring? So same spring, everything's the same, except what we're doing is we're going to double what V is. So if we double V, now we want to know what is the new X. So let's do C over here. Right. So for C we've got 1/2 mv squared plus mgh equals 1/2 kx squared. If I multiply everything by 2 and then divide by k and then take the square root, that'll be really nasty, but that's what we have to do. So I've got mv squared plus 2 mgh over k, and I take the square root, and that's equal to x. Right. Oh, I need to be careful here though because x is also h. Right. However much, if I'm kind of moving this around, then I'm also changing how high it is from the place where it ends. So I actually can't do that. So this is mgh, this is also mgx. Right. And I don't know what that is. So now, if I look at what I have here, this is going to be 0 equals kx squared minus 2 mgx minus mv squared. What I have is a quadratic equation. And since it's a quadratic equation, I plug in k, 2mg, and m. And what we're going to get, right, and for v I'm going to plug in 2 times the square root of 20, because square root of 20 was our velocity from before. And when you do all that, you should end up that x is equal to 0.079 or negative 0.077. And we're looking for the positive number, so it's going to be this. This is our new compression of the spring. Okay, and that's it for 7.7.